on the topic of anti-islanding protection and its requirements in the Australian context. So Winodh presented this, I believe, at the Australian Protection Symposium in August, so we're very lucky to have him present this again today. So just a bit about Winodh. He's a principal electrical engineer with over 10 years experience in generation and transmission systems. He's leading the protection and network connections team at the A office, and he has experience in designing secondary systems, power system modelling, protection studies, and power quality analysis. He also has extensive experience in connecting generation into the NEM, in particular with large-scale renewables such as wind and solar generation. So if you'd like to go ahead, Winodh, thank you very much for being with us today.
Thanks, Gav. Thanks, Emma, for the introduction. Welcome, everyone. So yeah, this webinar is really about anti-islanding protection and its requirements in the Australian context. Just want to thank my co-author as well, Samik Bhattacharya, based in the AECOM Brisbane office. There was a lot of research we had to do to finalise the paper and the presentation, so all his hard work is appreciated as well. Just in terms of the agenda for today, we'll quickly run through the network service provider requirements based on some of the key NSPs in Australia, both on the east and the west coast. We'd look at active anti-islanding schemes, which are primarily integrated into solar PV inverters. We look at the concept of non-detection zones, which is really associated with active anti-islanding schemes. Look at some of the equipment capabilities. Also touch on the requirements for modelling and how important it is to consider active schemes when doing modelling, in particular generator performance standards development. And also then provide a quick summary of the main points and topics discussed today. If you have questions, please hold them to the end. Happy to take the questions after the presentation. So just in terms of anti-islanding schemes, you can basically break it down into sort of two main implementations. You've got a local implementation, which you've got on the left there, and you've got a remote implementation. So things like remote implementations are a bit more complex and costly to implement because it requires communication between the local generating system and a remote facility, typically the network service provider's substation, for example. Once again, this presentation is really in the context of large-scale generators connected into the distribution system, or in some cases the transmission system. So large-scale, talking multi-megawatt size, so megawatt and above. So remote can be a SCADA or a direct trip, power line carrier or synchrophaser-based implementation of anti-islanding. And then local can be broken down into passive schemes and active schemes. So the passive schemes, everyone's probably quite familiar and used to that. Things like under voltage, over voltage, under frequency, over frequency, phase jump, vector shift, rock off, and reverse power. And then you've got the active schemes, which is really, I think, an area in Australia that's not really fully understood. So things like active frequency drift, Sandia frequency drift, voltage shift, and impedance measurement. So what we did next was we looked at the anti-islanding protection requirements that different NSPs have, and we pulled together a table just to see how they compare against each other. More in terms of, I think the main thing we got out of this was that the requirements do vary between the NSPs. So the items that are in red there are the mandatory requirements, and then the optional requirements really depend on the application. So it depends on the voltage they're connecting at, depends on the size of the generator itself, and it's really kind of addressed on a case-by-case basis. But generally speaking, you know, things like rock-off is required, vector shift it's quite often required. We've seen some cases where it can be negotiated out. So, you know, if you can say that, you know, there's quite often with vector shift we find nuisance stripping is an issue, and you end up changing your settings so much that the you know, it basically desensitizes it for a genuine islanded condition. Intertrip really varies on the application and the size once again, and typically under-over voltage is required, under-over frequency is required, neutral displacement depending on the application itself, and then you've got reverse power, directional kind of fault phase unbalance, and in some cases CBF. I think the main thing here is that there's a lot of functions required there, but with modern multifunction relays, a single relay will do a lot of this functionality. So gone on the days where you had to have a whole lot of discrete relays. But I think the key thing is when you're working on a project that you identify early what the requirements might be, and you specify your equipment to have this capability. It's a lot easier to have all the elements in that multifunction relay and turn them off or turn them on as required, as opposed to having to purchase additional equipment later on. So upfront, identifying that there is a risk with the embedded generator is probably the key point, and making sure you're fully across the NSP requirements. And I think there's probably some value here as well in terms of NSPs, looking at their different requirements and trying to be consistent across different areas. But that's an ideal case. Every network is different, so there are different requirements. But this, I guess, really goes to show how the requirements do change or do vary. Wanted to spend a bit more time talking about active anti-islanding schemes, because I think it's an area in Australia that's not necessarily covered in too much detail compared to overseas. There's a few different types. So there's the active frequency drift method, the Sandia frequency drift method, Sandia voltage shift method, which is typically used in conjunction with the Sandia frequency drift, slip mode frequency drift, network impedance measurement used in some of the old inverters, small string inverters, and measurement of impedance at a specific frequency. So the purpose of the presentation, we'll mainly talk about the first three items there, because they seem to be the ones that are used exclusively on larger scale inverters and also found to be quite effective. And so yeah, one more, the frequency jump method as well. Non-detection zone. So this is the concept of basically trying to quantify how effective an active anti-islanding scheme is. It's determined based on a quality factor, which is defined as resistance times the square root of capacitance on inductance, and this refers to the load characteristics. So you've got Q is a quality factor, load resistance, load capacitance, and load inductance. Generally speaking, a high Q value is challenging to detect. So this basically means a high capacitance or resistive load. So constant power loads, things like VSDs, are not typically challenging. It's typically the ones that produce a high Q value. I'll just go back to that. The reason this is important is quite often when you look at drop-off and vector shifts, there's not much analysis done around, confirming that, or doing studies to confirm that based on a particular scenario where you've got a generator connecting into a network, different load combinations are looked at, different contingency events are looked at and modeled to understand, is that drop-off going to operate, is the vector shift going to operate either correctly or incorrectly. So this Q factor, if you've got an idea of what the load is, and you've got some comfort for different types of loads, it doesn't matter if the load is exactly matched the generator size or the output at the time. If you know what the Q value is, through testing, you can get some comfort that for different Q values, and as long as the network at that particular location has a certain Q value that falls within that test range, you've got some comfort that the active anti-islanding scheme is going to operate. So the active frequency drift method, what is it? Basically, it's this. It's got what's called a chopping factor, which is defined as twice the TZ value, which is the 0 time. So if you look at that graph there, that's the time that the output is forced to 0. So what it tries to do is it basically tries to modify the output frequency of the inverter, for example. So under a strong grid scenario, it can't change the frequency, but under a weak grid scenario, it can change the frequency. So TZ is the 0 time for the active frequency drift signal, and T is the time for one cycle of the network voltage. The chopping factor determines the effectiveness of the scheme, and basically it's trying to force the frequency up or down until the under frequency or over frequency trips. The key thing here is that you've got to shift the frequency in one direction. It's got to either go up or down. There's no point having one set of inverters going up and one set of inverters going down. You want to get the effect that you're after. The non-detection zone is relatively large compared to the other methods. So that's one of sort of the I guess negatives of this scheme compared to the others. The Sandia frequency drift, very similar to the previous scheme, except it's got a bit of a gain that's applied to it. So the chopping fraction where there is no frequency error is the CF0 value, and then you've got this accelerating gain that doesn't change direction, but it tries to multiply the frequency error. So FA is your measured frequency of the voltage at the PCC, and FL is the line frequency. So it's an extension of the active frequency drift method. The chopping factor is a function of frequency error. So basically what it's doing is it's applying positive feedback to the frequency error. So it's trying to force the frequency change, and if it does change, if there is an error, it applies a positive gain to try and speed up that frequency change, basically. It's got the smallest non-detection zone, and it can be quite quick and effective. So I'll just move back to that one. So I think the key here is this K factor here, or the positive gain. So it's trying to basically continually apply that gain to the error. So as the error gets bigger, the difference in frequency between what's measured and what's output, it tries to increase that just to speed it up so it can hit the under frequency or over frequency limit a lot quicker. So just a bit of a comparison of the scheme. So you've got the active frequency drift, you've got the Sandia frequency drift and Sandia voltage shift. They're typically used in conjunction with each other. And you've got the slip mode frequency drift. So reliability-wise, and I think that's the key thing here with the active anti-Islanding schemes, is it's a bit of a compromise between reliability and power quality. So reliability in terms of accurately detecting a anti-islanded condition, and at the same time not resulting in spurious trips due to network events, for example, such as events or changes in on the network. So the active frequency drift, it's not very reliable due to the large non-detection zone. It has a reduction in power quality, in particular at lower frequencies, because it's trying to shift the frequency around the fundamental, and it requires coordination with other inverters, for example, making sure all inverters either shift up or shift down. Sandia frequency drift and Sandia voltage shift, it's very reliable, coupled with the Sandia voltage shift. It's got the smallest non-detection zone of all methods. It can have some effects on power quality due to frequency drifting, and some consideration needs to be given in terms of transient effects on weak networks due to inverter output instability, and I'll touch on this a little bit later. Can generally work with other inverters without coordination, and what we've seen is it's typically the scheme that's found on modern large-scale inverters. And then you've got slip mode frequency shift, where the non-detection zone cannot be eliminated. Main effect is on power factor, with no effects on harmonics. Can't operate with other inverters, and it's really this particular mode is just provided for comparison purposes. In terms of testing, so the question always comes up: if you've got an anti-Islanding scheme, how do you test it? How do you prove it works? And typically find that testing is not usually carried out. You know, the relays are tested in some cases, but how do you actually test the system works? So with an active anti-Islanding scheme, you typically have a setup like this. The setup's IEC is 62116, where you've got a inverter, which is your equipment under test, and you've got a power source, and you've got a monitoring, and you've got a load. And you've got a breaker as well there, vitamin green, which simulates the disconnection of the source from the inverter and the load. It looks at various RLC combinations, so we talked about that quality factor. So the intent here is to vary the RLC combination to have different quality factors. So if you know the equipment's tested for various quality factors and you know the quality factor of the load where you're connecting the project, you'd have a bit of comfort that that would detect that condition. The requirement is to disconnect within 2 seconds for those various RLC combinations. Let's go back to that one. So this is typically a test setup that's done in the lab. There's not necessarily any testing actually done on site. And we don't often see this requirement for this testing in documentation or in standards in Australia. So it's, whereas overseas in Europe, for example, it's really there and a requirement. Network performance impacts. Thought it was good to discuss the requirements of transmission versus distribution system connection in terms of anti-islanding. Typically in a transmission system, it's important to ensure that generators are connected and remain connected during fault events or contingency events. And islanding might not be as big a risk, whereas in distribution systems, islanding might be more of a risk rather than a requirement to, for example, ride through faults. So it's just understanding what's important in terms of the project that you're looking at. Is islanding really a risk or not? Or is the risk of nuisance stripping more a higher risk for the network than it is having an islanded system set up? So talking about system stability, islanding, those are 2 factors. Looking at weak network connections. In weak network connections, there is a bit of a concern around stability of control systems. And when you've got an active islanding scheme, which is really controlling the output, you want to make sure that that anti-islanding scheme or that algorithm is actually modeled. It's not always there when generator performance standard studies are done. So if you've got a PSSC kind of study, anti-islanding schemes aren't included in that. You really have to get something like a PSCAD model to make sure that the active anti-islanding scheme is actually modeled in there, and that there's no really adverse interactions between that algorithm and the overall control system itself. So we talked about a PSCAD-based model. So these are the ENT models that are required to ensure that the control system is stable. Equipment implementations. If you look at how the scheme is actually implemented, you've got basically this is the example of a PV inverter. You've got your PV source on the right-hand side. You've got your power bridge, which is your IGBTs, typically carrying out the switching. You've got the voltage, which is used to get the frequency measurements. You've got the anti-islanding algorithm, which produces a phase shift in the current controller. So the current's typically, if you're operating, for example, at a power factor of unity, the voltage and the current are in phase. So you introduce a current shift into your reference signal, which then signals the IGBTs to change output, and then you've got this feedback loop. And the idea is then you've got a over frequency or under frequency, passive element that's monitoring the output, and it'll hit its limits if there is now islanded condition set up. So it requires the controlling of the output quantities. The nomenclature of the actual anti-islanding scheme we found does vary between suppliers. So one of the biggest challenges is actually finding out what particular scheme is being used by a certain supplier in order to understand how effective or not it's going to be. Currently only on solar PV, but there's no reason why it can't be applied to Type 4 wind turbine converters as well, potentially Type 3 as well. We looked at capabilities of a few different suppliers. We've got one supplier's current generation of inverters. One thing we've also found is that depending on the type of scheme, they can either do active anti-islanding or fault right-through capability, but not both in some cases. Some inverters can, some can't. So that's an important aspect to consider if you've got an inverter that can only do one, but not the other, just knowing what the importance is. But ideally, they can do both, and you can choose to have either functionality switched on or off. So one manufacturer, they're using the escalating frequency drift, also known as Sandia frequency drift, and to active anti-islanding and fault right-through. That manufacturer's older generation wasn't clear what scheme they had, but you could only do one or the other. It couldn't do active anti-islanding and fault right-through, so you really had to choose which ones are most important. another manufacturer's current generation uses standard voltage shift. It wasn't clear if it could do active anti-islanding and fault right through or both. Another manufacturer had a implementation via the standard voltage shift, and it could only do one or the other. Another manufacturer with an older generation of string inverters used the impedance measurement technique, and that could only do active anti-islanding or fault right through and not both. So in summary, we found that the requirements do vary by NSP based on the anti-islanding requirements that they have. Passive schemes vary. Active schemes not always explicit, so it's not clear if they're required. The key thing, I think, is to know what the NSP requires early in the project, and understanding the active versus passive schemes and getting some comfort around non-detection zones and maloperation. Active schemes have evolved over time. The nomenclature does vary. The OEM implementations are quite different, so it's important to understand the OEM implementation and any limitations, and also what the biggest risk is for the project. Is it the risk of the islanding setup, or is it stability issues where low voltage right through is of importance? And lastly, the other area that we're really seeing a bit of development is stability, so stability of control systems, in particular in weak path network, where actual performance is not always evident in transient stability studies. So you really need to start with the control system stability, which is one of the issues for weak networks. And in that case, you really want to make sure that you've got your active anti-islanding scheme model, or the algorithm model, so as you do your analysis and look at various contingency events, you know that there's not going to be any adverse impacts. If there's going to be an island condition, the scheme will detect an island and disconnect, and also making sure that contingency events, that there aren't any instability issues as part of the control system. So look, that pretty much wraps it up. If you have any questions, happy to take them. I might just pass on to you, Emma, and yeah, we'll take questions and see how we go from there.
Oh, excellent. Thank you, Winodh. Look, I'll kick off questions. I have one ready. So I work for Energex. So in the Energex distribution system, we would have a fluctuating Q value over the course of a day, and on different days as well, weekday to weekend. And that's just because of different customers' usage behaviour. So would this change any implementation of these schemes?
Yeah, good question. And I think the key is probably understanding what that Q value range is. And what you can do is, if you look at a standard, or the test requirements, you can look at that particular inverter and see what Q value range it's been tested for. And if your actual, you look at the Q range that your network operates under, and that aligns with the, the test requirements that they've tested those various Q value ranges for, you can get some comfort that yes, the inverter would detect an island condition under that scenario and disconnect. And I think the key is just knowing what the Q value range is, and going back to the supplier and saying, look, can you provide some test certificates for successful operation of the anti-islanding scheme under this Q range?
Thank you. Does anyone have any other questions?
Okay. Yes, okay. David from Ergon here. Winodh, just wondering what your thoughts are on the recent changes to Australian standards for inverters, whether it's PV or battery, and particularly how they now have extra requirements for active anti-islanding and different test regimes.
Yeah, good question. I haven't gone through it in detail. I think the real focus of this presentation was looking at the different schemes that suppliers have, and just understanding what their capabilities and what testing they've done. I think overseas, the testing requirements are covered in that standard quite well. One thing that we looked at is we do a lot of connections kind of work, and one of the areas that we saw was that there wasn't clarity on, are these active anti-islanding schemes, are there software models for them to show, we're looking at stability studies. How do we get some comfort that there's not going to be any instability issues? So from a testing perspective, I haven't gone through the standard in detail, so it's probably an area to look at. But some of the discussions we've had with NSPs or some of the requirements that we've looked at, we haven't seen explicit wording on the active anti-islanding scheme and the requirements for test results. But I imagine over the next year or a couple of years that will change. I think the active anti-islanding scheme is probably a good way to go. But just making sure the capabilities of the equipment.
Yeah, that is something that we have. Yeah, that we're looking at, and Western Power and Ergon and Energix have made changes to that effect.
Oh, that's good. Okay. I think that's the right way to go.
Anyone else? You must have answered everyone's questions already, Winodh.
Yeah, I think that might be the case.
A good presentation.
All right, well, happy to take any emails, but yeah, I'll pass on to Emma. But yeah, if anyone has any questions, happy to take an email.
Excellent. Thank you very much, Winodh, for sharing that with us today. I know I've taken a fair bit out of it that I'll take back to my normal day-to-day job. So thank you very much for giving up your time.
No problem. Anytime.